Today we will continue our lecture on identical particle part 2. Here we are going to see the identical particle, three particle system, two particle system, as well as the identical particle including spin. In my previous class on identical particle, we have seen the wave function for two particle problem. We have seen the wave function for symmetrical and anti-symmetric. And now we will see the exchange degeneracy. The total wave function for the symmetrical case is equal to 1 over square root 2 times psi A of R1 psi P of R2 plus psi A of R2 and psi P of R2. This we have seen in my earlier class. And if it is anti-symmetric, this plus will become minus. However, both will have the solution uh, correspond to same total energy eigenfunction. These two are having the same total energy eigenvalue. So this is the degeneracy, same energy with a different state. This degeneracy is called exchange degeneracy. That is one important point. For a symmetrical system, the total wave function is 1 over square root 2 psi A of R1 and psi P of R2 plus psi A of R2 multiplied by psi P of R1. This can be written in the summation form that psi sub s is equal to 1 over square root 2 summation over P uh, get P cat psi A R1 and psi P R2. Here, P cat is the permutation operator. See, in previous class, I have used P for the exchange operator. Particle exchange operator. Here, it is not particle exchange operator. Of course, we are using same symbol. So, this is a permutation operator where the sum is over all possible permutation. Here, the only two possible permutation, only two. So, similarly, in similar manner, we can write the uh, total wave function for anti-symmetric case, which is equal to 1 over square root 2 summation over p minus 1 power p psi a of r1 and psi p of r2, where minus 1 power p is equal to 1 for even permutation. That is when we interchange both R1 and R2 and also psi b, psi A and psi B. And it's equal to minus 1 for an odd permutation. That is when we permute R1 and R2 but not psi A, psi B and vice versa. This is the anti-permutation. It is one per permutation. Then this is one per even permutation and minus one per odd permutation. Just now we have seen that the anti-symmetric wave function can be written as a summation form. Same thing we can write in the uh, determinant of a matrix. Here psi sub A, that is total wave function anti-symmetric case, is equal to 1 over square root of n factorial. Here we have taken two particle system, so this 2 factorial is 2. Then determinant of the first column is for particle A and the second column is particle P, and first row is for particle A, second row is for particle P, and first column is for coordinate system R1 and the second column is for coordinate system R2. Now, this since n factorial is 2, we can write like this. Now you can this determinant of this one is psi sub a r1 multiplied by psi p r2 minus psi sub a r2 psi p r1. So we can write this in the matrix form like this. Uh, this determinant, we are seeing the determinant. This determinant is called the Slater determinant, where we got automatically the negative sign. Uh, we will understand in still in better way when we are dealing with the three particle system. And now we will see for three particle system. For three particle system, the symmetric wave function, total wave function, symmetric wave function is equal to 1 over square root of 3 factorial summation over p, p cat psi a of r1, psi p of r2, psi c of R3, where P is the permutation operator and where sum is overall possible permutation. We can use all possible permutation, which can be written as psi sub s is equal to 1 over square root 6. That is 3 factorial is 6. Uh, then psi 1 2 3 plus psi 1 3 2 like this will go like this. See here first two term you take it. Psi 1 2 and 3 here 2 and 3 will get exchanged. So this will become 3 and 2. Similarly here, psi 2, 3, 1 is a cyclic. So 3 and 1 will get interchanged. So psi 2, 1, 3. 3, 1 will become 1, 3. Similarly, psi 3, 1, 2. 1 and 2 interchanged. We are exchanging 1 and 2. So 2, 1 will come. Here, psi, capital psi 1, 2, 3 is equal to psi A of R1 and psi P of R2, psi C of R3. So this is the meaning. I have written this in a simple notation in order to make it very simple. Say, for example, you take this one, third term, then it is equivalent to psi A R2 and psi B R3 and psi C R1. In that way it will go. So it's a simple way of writing things. Uh, then we will see what about the anti-cyclic wave function. For anti-symmetric case, we will use like two particle problem. We will use for three particle the Slater determinant. You know, just now I have explained what is Slater determinant. So the anti-symmetric wave function is equal to 1 over square root of 3 factorial and the determinant of this matrix. Here, the first row is for particle A, second row is for particle P, third row is for particle C. In order to make things simple, I used R1 as simply 1, R2 as simply 2, R3 as simply 3. So the first column is for R1, second column is for R2, third column is for R3. So this is if you find the determinant, what you will do, you take psi A1, then psi B 2, psi C 3. So that is the first term, this one. Then next, psi A1, matrix multiplication, determinant, you want to find the determinant, psi A1 minus psi B3 psi C2. So this one minus. So in that way you will get plus and minus. I have explained the meaning of psi 1, 2, 3 and psi 1, 3, 2. So for a three particle system, you can write the wave function in terms of Slater determinant. That is one important thing. Now, so far we have ignored the spin of the particle. If you include the spin, then what will happen? See, we can separate the wave function into two parts. Psi of r, chi s, where psi is the radial part of the wave function and chi is the spin part of the wave function. Now we will see about the system including the spin. Before going into the detail, we will see the spin of the composite particle. We know so far we have seen for fermion spin is half integer, for boson it is an integer value. Now we will see what will happen to composite particle. Say for example, if composite particle contains even number of fermions, say 2 or 4 or 6, even number of fermions, maybe electron or proton, and any number of bosons, it behaves like as a boson. So if it is even number of fermion, even though it is fermion, say let us say, take simple case, 2 fermion, each will have spin up, spin half. So if you add both, you will get to spin one, which is the behavior of boson. So if you have two fermion and any number of boson, then that system behaves like a boson. And if it contains an odd number of fermion and any number of boson, boson we know is having the spin of integers. It behaves like fermion. This is very crucial point. Let us take helium 4 for example, which has two proton and two neutron in the nucleus and two electron, and naturally is a boson because you have two electron as well as two proton. It exhibits the bosonic superfluidity. Then similarly, if you consider helium 3, which has two protons and one neutron in the nucleus and two electrons, and it is a fermion. So because in the nucleus you have add number of fermion, so naturally it is helium 3 is behaves like a fermion. Now consider the helium atom at ground state is a two particle system. So the total wave function capital psi 1, which is a function of r1 coordinate r1 and r2, is equal to small psi chi. Chi is the spin wave function. This can be written as psi sub a of 1, psi sub b of 2 chi. So this antisymmetric wave function can be written as 1 over square root of 2 using the Slater determinant. Determinant, the as usual, the first column is for spin up particle alpha, and the second column is spin tau. So if you take determinant, you will get psi a of 1 alpha, this one, and psi p of psi p2 of beta minus this one, psi p 1 of alpha multiplied by psi a2 of beta. Here I like to highlight one important point. If total wave function is symmetry, either anti-symmetry, either wave function part is symmetry and spin is anti-symmetry, or wave function is anti-symmetry, spin is symmetry. Both cannot be anti-symmetry. If psi and chi are anti-symmetry, so anti-symmetry multiplied with another anti-symmetry, you will get a symmetric wave function. So either radial part of the wave function and spin part of the wave function must be anti-symmetry in order to have your total wave function as anti-symmetry. Here I have mentioned psi s comma a. This means first one is the radial part. Radial part of the wave function is symmetry. Next one is spin part, which is anti-symmetry. So I can write this as psi s 1 over square root of 2 alpha beta minus beta alpha, because this spin wave function is anti-symmetry. So that is the meaning of psi sub s comma a, which is equal to psi s radial part of the wave function, which is symmetry, 1 over square root of 2 alpha times beta minus beta times alpha. We have taken the helium atom as our example. In helium atom, we have two electrons. That is, spin is half plus half. Total spin is 1. This get vector can be written in the conventional way, yes, ms, where ms is the spin quantum number. So if s is 1, then you know very well that spin quantum number varies from -1 to +1 in step of 1. So uh, there are four possibilities. That is, both both electrons are at spin up state. Then ms is equal to 1. Then when ms is equal to 0, uh, one spin is up state, other one is down, or one is down and the other one is up. In both cases, the magnetic spin quantum number is 0. Similarly, both are down, then the magnetic quantum number is -1, because both are down. But S value is 1 for all the four cases. Now you come to this. The parameter I have written in the blue color rectangular box. First case, the S is 1. So, of course, in all four cases, S is 1. Then in this case, M is also 1, both are up. Then here ms is 0. So there are two possibility, ms 0. There are two possibility. One spin up and spin down, other one is spin down and spin up. So if it is symmetry, you can add this spin. Up down plus down up. This normalization constant is 1 over square root of 2. If both are down, here also m is s is 1. So then m is -1. So both are, when both are down, you have this triplet state. This state is triplet. Uh, because S is 1, MS is -1, 0, 1. There are two possibilities. Here we have taken the symmetry wave functions. The spin part of the wave function is symmetry. There is another wave. Spin wave is anti-symmetry. Then you will get minus, because there are two zero. Here also it is 1 0. But however, the spin up, spin down, because it's plus up minus up 0. Here also 0. This is 0 minus 0. So it is indicate that it is anti-symmetry. So this singlet state is called parahelium, and this triplet state is called orthohelium. So since there is ms is equal to 0, two cases, we will write like this. One is the symmetric one and the other one is anti-symmetric. Here we have taken all are symmetry, because both here no question of symmetry, because both are up, here both are down. So it's a symmetrical one naturally. Here also we are adding symmetrical one. Here it is anti-symmetry, which is called singlet parahelium. This is triplet orthohelium. Thank you very much for watching my videos and supporting me continuously. Thank you very much.